When your laptop runs a heavy task, you can literally feel it heat up as the processors work. But the most powerful processors on Earth don't sit on a warm desk. They are suspended inside a freezing, isolated glass case. To understand why, we have to look at how regular computers solve problems. They use bits, information stored as zeros and ones. Think of a normal computer trying to solve a maze. It traces one path, hits a dead end, turns back, and tries another route. It checks every option one by one. Quantum computers use something called qubits. Because of a quirk in physics called superposition, a qubit can be a 0 and a 1 at the exact same time. Instead of choosing a single route, it walks down every single path in the maze at the exact same moment. It skips the whole trial and error process. By operating under different laws of physics, it completely bypasses the limits of traditional logic. So if they are that capable, why aren't we all using them to browse the internet? Think of a computer like a soccer player. Regular computers play by the standard rules, using their feet. They are the perfect tool for everyday tasks, like sending emails or playing videos. Quantum computers are like picking the ball up with your hands. You wouldn't use your hands to run down the field, but if you need to catch a highly complex, fast-moving problem, using your hands is much more effective. They are highly specialized tools, built strictly for problems that normal computers literally do not have the rules to solve. One of those difficult problems is finding new medicines. A molecule is essentially a chemical puzzle with billions of possible structural combinations. When physicists like Richard Feynman first dreamed up these machines, they realized standard computers get overwhelmed simulating the complex, overlapping structures of nature. We are beginning to see the first real-world results of this vision. Researchers recently used an IBM quantum computer to find a molecule that blocks a specific protein, the KRAS gene, which is known to cause cells to grow out of control and form tumors. While these are still early experiments, they suggest a future where we move away from slow trial and error and toward a system where we can engineer life-saving treatments with mathematical precision. If they are so promising, why aren't these machines everywhere yet? It comes down to temperature. To work, these systems require a device that looks like a golden chandelier called a dilution refrigerator. It drops the temperature around the processor to nearly -273 degrees Celsius, colder than the empty vacuum of deep space. The cold is necessary because qubits are incredibly delicate. The tiniest trace of heat or the microscopic vibration of a footstep shatters their quantum state. Because they are so fragile, engineers are currently trying to achieve something called fault tolerance. This means building a system that can automatically detect and fix its own delicate errors as they happen. Solving this error problem will allow these machines to move from the lab into the real world as stable industrial powerhouses. The potential rewards, from medical breakthroughs to the ability to crack global encryption, have triggered a massive international race. Governments are mobilizing enormous money. The US committed over $1 billion, while Europe and the UK back multi-billion-dollar strategies. In Asia, the scale increases. China is directing $15 billion, and Japan targets 10 million users by 2030. Alongside governments, the world's largest tech companies are competing to build perfectly stable, reliable systems. They are working to control the economic and security infrastructure that will define the century. Despite all this effort, you will likely never have one of these machines on your desk. But you will see the effects in more accurate climate models, secure banking, and faster drug discovery. Our ability to solve these global problems relies entirely on harnessing the strange, cold rules of quantum physics. What we are seeing are the first signs of a world built on new physical foundations.